we now come to our third radioactivity video clip, and this one is about atoms, elements, isotopes, and the numbers that we find associated with each particular atom. So, for a start, if we consider carbon. Now, carbon, atomic symbol C, has an atomic mass normally of 12 and an atomic number of 6. That atomic number at the bottom, always the smallest number at the bottom, tells you that it has 6 protons. Now, if it's carbon as an atom, it will also have 6 electrons. If it's been ionised and it's got a plus at the top, that means it's missing an electron, so that would be down to 5. If it has a minus at the top, that means it's picked up an extra electron and it would be 7. But as a neutral atom, as this one is, we have 6 protons and 6 electrons to balance it. The mass number up here is 12, which tells us, of course, that we have 6 protons, but 12 take away 6 leaves us with another 6, so we must have 6 protons and 6 neutrons, because the mass of an electron is so small it doesn't have any effect on this. If, however, we come across carbon-14, which is the radioactive isotope of carbon, has a mass of 14, hence the name, still has 6 protons, otherwise it wouldn't be carbon anymore. And since it's not been ionised, it's also got 6 electrons. But now its mass has been increased, so we've got 6 protons, but 14 take away 6 leaves us with 8, so we must have 8 neutrons. And that is why these two atoms, although they're both carbon, we know they're carbon because of the symbol C, we know they're carbon because of the 6 here. 6 protons is always carbon. They're not ionised, so we also know they have 6 electrons in both cases. But the different number at the top, the mass number being different, shows us that we have 2 different isotopes. And to find out the number of neutrons, we take the mass number, we take away the number of protons. In this case, 12 take away 6, this is with 6 neutrons. 14 takes away 6, this is with 8 neutrons. And carbon-14 is a radioactive isotope of carbon. Carbon-12 is relatively stable, certainly stable in the timescales that we're going to talk about for GCSE. Now, the other thing I want to talk to you about in terms of those numbers is how they change in radioactive decay. There's only 3 different ways that at GCSE we consider atoms changing in radioactive decay, giving off alpha or beta or gamma radiation. So there's only 3 to remember. Now, if we take carbon-14, and we make it undergo a radioactive decay, it's going to decay into a stable isotope of nitrogen by giving off a beta particle. Now, we know that a beta particle is an electron, we talked about that earlier, so it has a charge of -1 and it has a mass of very nearly 0. So make it 0 for these sorts of calculations. Now, if we treat that arrow like an equal sign, we see that 6 is going to be equal to something -1. Well, I think we can all cope with the idea that that must be 7. And that's good because the atomic number of nitrogen is 7. And the mass, well, the mass hasn't changed at all. So it's nitrogen-14. So beta decay always leaves the mass as it was and increases the atomic number by 1. There's 2 other types of radiation that can be given off. Let's consider that our carbon-14 is replaced by uranium. uranium-235. With an atomic number of 92, a mass of 235. So that means that there are 143 neutrons. 235 take away 92. Uranium will decay through an alpha decay. Alpha has a mass of 4, 2 neutrons and 2 protons, and a charge of +2. That means that our new element must have a mass of 235, take away 4, treat the arrow like an equal sign, 231, and an atomic number of 90. And that, I believe, is radium. But if they need you to work out which atom it is, they'll give you a periodic table. The numbers you can follow. And I've saved the best till last. Let's consider our nitrogen at the beginning. Nitrogen 14(7). It's decayed from carbon 14(6). Well, let's imagine that the protons and neutrons in the nucleus still have a bit of energy left over. And they decay a little bit further by just getting rid of that excess energy using a gamma ray. Gamma rays have a mass of 0 and a charge of 0, which means neither the mass nor the atomic number has changed. We must still have nitrogen, and it must still be 14(7). Easiest piece of math you're ever going to find. 14 is equal to 14 plus 0, 7 is equal to 7 plus 0. So, you need to remember that the number at the top is the number of protons and neutrons, and that can vary depending on whether or not you've got an isotope. You need to remember that the bottom number is the number of protons, and if you don't have an ion, it's also the number of electrons. You need to remember that beta decay decreases the mass by nothing and increases the atomic number by 1. What actually happens is that one of the neutrons in the nucleus turns into a proton. You need to remember that in alpha radiation, the mass goes down by 4 and the atomic number goes down by 2. And you need to remember that in gamma radiation, the mass and the charge do not change. So the atom remains the same, but it's given off its excess energy. Those are the 3 examples you're going to have to look at GCSE. Each one leads to a more stable atom. If you're given the type of decay and the starting or the ending atom, you can work it out. If you're given the starting and the ending atom, you can work out which type of decay took place. All you need to do is look at the numbers at the top and the numbers at the bottom. If the number at the top doesn't change, it's either beta or gamma, but if the number at the bottom doesn't change either, it's gamma. If it does change, it's beta. If the number at the top changes, it's alpha. Simple as that. Good luck.